electric potential and electric P. This is the topic we are doing right now. And electric potential is same as gravitational potential. First, we need to define electric potential, and obviously we have to define the absolute value in which the reference will be the infinite point. So electric potential is defined as it is electric work done in bringing a unit positive charge from infinite point to a point in electric field. So electric potential is basically electric work done in bringing a unit positive charge from infinite point to a point in an electric field. Now, in case of attraction, the formula for work was, for example, previously we written formula for gravitational work. Formula for gravitational work, if you remember that, when an object is moved above the earth, it was capital G smaller m capital M into, it was 1 over R2 minus 1 over R1. If in case of attraction, you are calculating electric work, it will be 1 over 4 pi epsilon naught smaller q capital Q into 1 over R2 minus 1 over R1. And it could be calculated for repulsion. In case of repulsion, the formula will change. In case of repulsion, the electric work will be 1 over 4 pi epsilon naught smaller q capital Q into 1 over R1 minus 1 over R2. Now, if we define the variables that we used, we must know that the variables that we are using in this formula, they represent what we have to see. They are representing basically, first of all, smaller q is the moving charge, capital Q is the still charge, R1 is the distance of the initial point from the charge, and R2 is the distance of the final point from the charge. So this is the whole story. Now, if we move on, for example, if we go with electric potential of a positive charge. We want to write the electric potential of a positive charge, then we should know that there's a positive charge capital Q, and here we get this point is, for example, uh, this point is, for example, infinite point. This point is, for example, infinite point. Now, at infinite point, the electric potential is represented by symbol V basically. At infinite point, the electric field strength is 0 and electric potential is also 0. Now, if we take a charge of +1 coulomb at infinite point, you see the distance of infinite point from this charge will be, this is the initial distance and it will be infinite. So we are starting from the infinite distance. And then this charge is moved to a point P, which is, for example, this charge is moved to a distance to a point P, which is at a distance of, for example, smaller r from the positive charge. And smaller r here represents R2. So if we calculate electric work in the given situation, we should know that smaller q is +1 coulomb, capital Q is capital Q, and R1 is infinite, R2 is R. Now if we substitute the values, it would become work is equal to 1 over 4 pi epsilon naught smaller q capital Q into 1 over, it's a case of repulsion here. So it will be 1 over R1 minus 1 over R2. Now if we substitute the values, it will become work is equal to 1 over 4 pi epsilon naught smaller q is +1 coulomb, capital Q is capital Q, and then it would be 1 over R2 is 1 over R1 is 1 over infinite minus 1 over R2 is R. So finally it would become 1 over 4 pi epsilon naught capital Q times minus 1 over R. So it is minus 1 over 4 pi epsilon naught capital Q over R. If the electric work is negative, then the change of electrical potential energy will be positive. For example, since the work is negative here, so electrical PE will increase. So we must write the electric work is negative. So the electric work is negative. So electrical PE will increase, and electrical PE of plus 1 coulomb charge electrical PE of plus 1 coulomb charge is called electric potential represented by V. So as a result, we can say that V is equal to delta P in the given example, and that is equal to negative of work. Hence, we can say that negative of Q over R. So the final answer will be plus 1 over 4 pi epsilon naught Q over R. So this is the formula for electric potential of a positive charge. 1 over 4 pi epsilon naught capital Q over R. Capital Q is a charge and R is the distance from the charge. Now, what if same formula is written for a negative charge? Now, if you have a negative charge and you want to write the value of potential at a distance R from this negative charge, again, you start from infinite point. At infinite point, the potential energy of plus 1 coulomb charge will be 0. For example, at this point, the potential will be 0 and the potential energy will also be 0. The potential and the potential energy both will be 0 at the infinite point. Now, if you move a charge from the infinite point to point P, from the infinite point to point P, then work in this case, in fact, negative of work in this case will represent the electric potential, given that the charge moved is positive 1 coulomb. So the charge moved is positive 1 coulomb and the work done will be electric potential. So we should say that first of all, it's the case of attraction. Since it is attraction, so the formula would be work is equal to 1 over 4 pi epsilon naught smaller q capital Q into 1 over R2 minus 1 over R1. Here R1 is infinite and R2 is R. Now, if we substitute these values into the main formula, it would become work is equal to 1 over 4 pi epsilon naught smaller q capital Q into R2 is R and R1 is infinite. So finally, it will lead to 1 over 4 pi epsilon naught smaller q is plus 1 coulomb, capital Q is Q, and then it is 1 over R. So it will become 1 over 4 pi epsilon naught capital Q over smaller r. This is the formula for work, and the work is positive, which means that PE is decreased. So electric potential represented by V in this example will be equal to, obviously, change of potential energy, that is equal to negative of work. And the formula will become V is equal to negative of 1 over 4 pi epsilon naught capital Q over smaller r. So we have two formulae, one for the positive charge and one for the negative charge. We can say that for the positive charge, V is equal to 1 over 4 pi epsilon naught Q over R, and for the negative charge, it would be V is equal to minus 1 over 4 pi epsilon naught Q over R. So this is for the positive charge and this is for the negative charge. And these are the formulae for potential. These are the formulae for electric potential. Now, electrical potential energy will be equal to Q times V. Q will be the charge moved and V will be the potential at a point. And delta electrical P, or change of electrical P, will be equal to PE2 minus PE1. So it would be, in simple words, Q times V2 minus Q times V1. If we take Q common, it could be written as Q times V2 minus V1, or Q times delta V. Or we can say it is Q times delta V. So, in other words, if we say if an electron moves in the field of alpha particle, then the change of potential energy will be charge on electron and delta V of alpha particle. Students, from here on, we are starting in the next slide, inshallah. Take care until then.